In this video, I want to talk a little bit about sketching functions. And now I say sketching functions here, not graphing functions. If I want to graph a function and I want it to be very accurate, I go to a computer, as should everyone else. But I want to talk about sketching functions because that plays a different role in what I'm talking about. This plays a role in moving between different representations of a problem to help solve it. So let me describe what I mean. So if I say there's a function where the output of the function is the square of the input, that is a verbal representation of a function. So we can say here he's talking, and I could write it out, but writing it out is also a way we call the verbal representation of a function. So talking, a function whose output is the square of the input, that is a verbal representation. Now, if I wanted a mathematical representation, I might write that as this. So the input is x, the output is x squared. This is a mathematical representation. They're a mathematical representation of the same thing. And so now what I'd like is a graphical representation. A graphical representation. And I don't want to have to fire up my computer because I just want to be able to sketch what a graphical representation of what that function is. And so I would have here x, f of x, and we say, so here's 1, we'll call this 2, 3, oop, I wanted to spread it out a little bit. 1, we'll call that 1, 2, 1, 2, and so then if we have, there's 1, 2, 3, 4. So I want to represent that graphically. I have at x is 0, f is 0, 1 is 1, 2 is 4, and then I can sketch that graph. So sketching the graph gives me a graphical representation of a mathematical representation. It's a graphical representation of my function. As a physicist and taking a physics class, you have to be able to go between these types of representations. And in fact, when solving problems, very difficult problems, when you get stuck or you're trying to figure something else out, looking at the problem from different representations is a very powerful method to help you solve problems. All right, so that's what I mean by sketching functions is really sort of this graphical representation. So let's do some important examples of different types of functions. So the first type of function I want to look at is 1 over x to the n. And in this case, I'm going to look where x is greater than 0. So I'm just looking for positive at the moment, and n is greater than or equal to 1. So 1 over x and higher powers of 1 over x to the n. So what does that look like? So I have a graph, sketch this graph. So here's x, and here's f of x. The most important point, and so I'm looking for important points, just like before I looked at x is equal to 0, etc. My most important point here, I think, is where x is equal to 1 and f of x is equal to 1, because I know then that all of my functions are going to go between that point, because 1 to any power is 1. So that's the first part. You look at a function, you want to sketch it, you want to find important points on the graph. So if I were to sort of draw a diagonal that splits the my curve here at 45-degree angle. And my first graph I'm going to draw is just n is equal to 1. So for n is equal to 1 is just 1 over x. What does that look like? Well, it's symmetric on this graph. And so it's going to go to 0 as x goes to infinity, and it goes to infinity as x goes to 0. Right, so it goes to 0 as x goes to infinity, and the function goes to infinity as x goes to 0, and it does it symmetrically about this dashed green line that I had here. So that's what f of 1 over x looks like. What happens for n is equal to 2? So that's fx over 1 over x squared. So we can do this in blue. So what does 1 over x squared look like relative to 1 over x? Well, as x gets large, x squared is much larger, which means f of x goes to 0 faster than x does. And it goes to infinity faster than 1 over x. So it might look like this. And so for n is equal to 3, which is f of x, so 1 over x cubed, the same thing. So it goes to infinity, it goes to 0 faster as x goes to infinity, and it goes to infinity faster than, it doesn't go back though. It goes to infinity faster than the others. And that continues. So the higher the value of n, the faster to 0 goes the function as x goes to infinity, and faster the function goes to infinity as x goes to 0. So that's a characteristic of this entire class of functions. So if you have, say, a combination of functions, say, of some constant x of x squared minus 1 over x to the fourth, then you can then compare how these functions behave and how they compete against each other at large and small x. But so anyway, so that we're not going to get into that right now, but that's sort of a looking at the class of functions 1 over x to the n. Let's look at the exponential function. So I want to consider x of time, so x of t, e to the minus t over 2. So what does this function look like? Have t go out here. And sometimes you don't really know what values. You have to plug in a couple values to see what something might look like. Is t is equal to 0, of course, x is equal to 1. E to the x of 0 is equal to e to the 0 is equal to 1. And so since I have this t over 2, I'm going to look at x to the 2, which is e to the minus 1, and x to the 3, I'll write that as 1 over e. Let's go x to the 4, then e to the minus 2, which is 1 over e squared. If e is about 3, then this is 1/3 and this is 1/9. So I can starts at 1, and by 2 it's going to get to about 1/3, and then by 4 it must get to about 1/9 of its original. So about here and about here. And so we have, it's not a very good exponentially decaying function. A little tough to... So my exponentially decaying function looks something like that.